First of all, welcome everyone. Thank you for being here. And welcome Professor Peszynska to be here. Okay, Malgorzata Peszynska. Short Malgo, because it's a bit easier to than the full name. So I just want to introduce the speaker today. She has like a lot of like scientific achievements, so I will just point on some of them. You can see the full list on the web page. So Malgo received a Ph.D. in mathematics at the University of Augsburg some years ago.
In the past century.
Then also you had like academic position in the Polish Academy of Science, Warsaw University, Purdue University, University of Texas at Austin, and now since a while in Oregon State, 2003, and then you became full professor, 2012. And then you really have like a lot of achievement that you got, and one very important is that you really had like a leadership and service position at the SIAM, and also the president of the SIAM Pacific Northwest section and SIAM Geoscience for some many years. Many students, many postdoc, many researcher, and yeah, so today you are here to present your research, and thanks a lot for being here.
Yes, thank you. Can you hear me okay? I'll try to use my teaching voice. I don't start classes until next week, but yeah, tell me if I'm not speaking loud enough. So thank you for inviting me and everyone for being here, and especially Alessio, Anna, and Luca alphabetically for hosting the so wonderfully. I will share with you sort of a big picture of a lot of things that myself and the collaborators, including students, have been working on. But maybe I'll start with the motivation. Okay, this one has taken over. Okay, so you might know the saying, "What happens in Vegas stays in Vegas." If you saw the movie, you know why. But this is a phrase that was coined by a science group that I participated in about the Arctic. So in here, well, in a minute, you will see an alligator behind my postdoc. And we're at a conference in Florida. And what happens in the Arctic will eventually also affect people living in Florida and these alligators, no matter what a lot of people say these days. I will be talking about a lot of the multi-things, so multi-physics, including multi-phase and multi-component elements. I'll be talking about things happening at multiple spatial and temporal scales. And you will see that a lot of the dynamics of what we're describing, of course, depends on the environmental conditions. And it does affect the environment back, but that's not what I'm going to be talking about. And being mathematicians, we always like to come up with first the study of, well, positiveness of the models. And the models I work with are PDE, partial differential equations based. But a lot of times for coupled problems, there's not that much that you can do in terms of analysis. So you analyze sub-problems, you now analyze convergence of schemes for sub-problems, but you can't really go too far. So you always have to trust that the components are good, and then that you put them together in the correct way. Yeah, and of course you have to use the right data. Being a mathematician, well, I got my degree at Politecnico in Warsaw, but I frequently struggle with the units, and occasionally, you know, if you plug in a unit of a particular quantity that's like 3 degrees of magnitude off, then your code either works beautifully or doesn't, depending on what you did. And so data is important, and also variability of data is important. So here's a picture of some of people from my group, in particular with Anna Tchaikovsky. we've done a lot of work at modeling fluids from pore-scale to Darcy scale, including Forchheimer. I know a lot of people here and students presented things on Darcy and Forchheimer, so we did a lot of modeling, trying to understand what form of Forchheimer wants to do. Here are a lot of different students. Here's the postdoc I mentioned, and right there is the mentioned alligator. So I don't know what will be the future of people walking in a park in Florida, whether the alligators will disappear or rather become more aggressive. But at least 2 years ago, we were still able to do that. So yeah, okay. So lots of collaborators from math and also from geosciences. We had a lot of colleagues from the College of Earth, Ocean, and Atmospheric Sciences who kind of coerced me to work on some of the problems. Yeah, out to them, gratitude, and also, it wasn't too easy to find the common languages, and I know that you are all very successful doing it here, finding collaborations with geoscience. So great. All right, so what I will be talking about today in different pieces, you can see the outline more or less on top, is coupled processes that involve thermal processes with P, that means phase change, and that's the important component of it. Hydrological, so flow, Darcy flow, or at the pore scale, it's the Stokes flow models. And then N is mechanical. You will see some progress that we have made in working from pore to Darcy scale there. And then C is for chemistry, but yeah, you will see that's mass conservation, but has different flavors than just the flow models. And then we'll be working across the scale. So this is, you can see the North Pole is somewhere there, not in the center, as you all know, right? But around the North Pole, there are terrestrial portions of the Arctic covered by permafrost. So what in dark blue are areas covered by permafrost soils, and I'll talk a little bit, well, actually quite a bit about that. This is a different scale. You see, obviously, the scale we intended to work on. This is more of a 1 meter scale. This is the pore scale, with some simulations under mechanical deformation. And this is the view more closely of the interface scale. So this is the kind of an image that we get from colleagues who work on imaging porous media. You see here in white, the grains of porous media. So this is, by the way, not true porous medium. This is glass beads, which are transparent, so it's fairly easy to visualize fluid. And in black here, you see a different phase. So in this case, this was biofilm, but people have done some studies also with ice. Now with ice, of course, very difficult, or methane hydrate, difficult to image this kind of a region because you would have to maintain the temperature and pressure conditions at which these substances and different phases exist. So a lot of the stuff we do in modeling is because you can't really easily conduct experiments and visualize, and then they come up with statistical correlations between the phenomena. So models sometimes are the only thing you can do. Now, what we do in what I will present in this talk is based on our discretization on rectangular grids. And the reason being is that our grids, we want to have models that will work well across the different scales, starting at the pore scale. And you always have voxel, you say voxel grids, so pixel grids at the pore scale. And so naturally, also, we want to have conservative methods. So our choice has been the lowest order mixed finite element method, Ravier-Thomas, which are also then known as the self-centered finite differences or finite volumes. This fits to what we work on because our solutions to the PDEs have very low regularity, and then the complexity of the physics is so high that frequently students who, and myself working on the projects from the beginning, really want to work on IJK, at least for the moment. And then sometimes we hope to move on to higher order methods, and I hope to have some collaborations, maybe with some of you who can do that very well. But for a long time, that has been, we sort of got stuck there and moved on with the physics. Another reason why the rectangular, let's say, cell based grids are really useful is because you can easily merge the results or compare the results with things like Ising models or Potts models and Markov chain Monte Carlo method. So we have resorted to sometimes to simulations that are not just traditional physics simulations, but sometimes we use these other methods because the complexity of the physics is such that sometimes it makes more sense to do these. So this is the overview. All right, now here's an example. This is probably the only theorem you're going to see really stated like this in the talk. This is an example of what we can do for a couple of models. This one is on biofilm. So C2 means there are two components, biofilm and nutrient, coupled to Stokes model. Right now, we also have some ongoing work with Brinkman flow. And you see here some simulation results with black being the grains. And what you see here is microbes that aggregate and form biofilm. You see here how those microbes like to stick together and how flow paths change. And at some point, the pore-scale gets clogged. Now, what you can prove is at best first order accuracy. And so making a lot of assumptions on the regularity, we solved this problem using it's a parabolic variation and equality system. So there are some constraints. We use the technique of various techniques, but one of them came from the working course median for Richards equation. All right, so one can prove a lot of different things, but the key is how do you incorporate a lot of different physics? All right, so going back to what I want to talk about is that permafrost, you already have seen this region. A lot of permafrost, so permafrost is soils that are frozen for quite a long time. Permafrost exists not just in the Arctic, but also this is an image 2 years ago from a village, Bondo in Switzerland, where due to permafrost thawing, there was a big landslide. And there was actually a recent one as well. Everybody was watching what was going on. I just don't have a picture here. So we want to understand how the change in the global temperatures is affecting more and more this thawing. To do that, we resorted first to understand how things go from pore-scale to Darcy scale. And then here's another motivation why you would want to study the different processes. So in the Arctic, you see a lot of landslides. The coastal erosion is progressing. About 1 meter of coastal line a year is what people are observing in the Arctic, which means whole villages in Alaska in particular have to be moved inland because they all of a sudden are on islands rather than on solid land. And you see subsidence, so typical things that are happening to infrastructure. Here you have a picture also of how presence of vegetation or absence of vegetation may affect the permafrost. This is an image from Russia, so from Siberia. Anyway, the idea is you want to study a lot of these coupled phenomena. But the question is, where do you get the constitutive loss? Where do you get the data? And this data is sparse. So now talking about microscale, here's a picture maybe of a soil in permafrost region. So you have the grains in black, you have water in both phases, ice and liquid, and you may have some pockets of air. There exists also something called dirty snow, cryoconite, very present in Nepal and other places. The more rock you have, the more it thaws. There's also a lot of dirty snow, for example, around Detroit in the United States. You know why? Because there are particles of carbon that are deposited there. So the snow is melting more, so it's not melting faster, and so on, so on. So the quantities that we use to describe these different complicated multi-phase, multi-component places are porosity. So that's the proportion of void space with respect to the entire space. I wrote some numbers here. If you are quick in counting, you can count if I did this right. The liquid fraction here would be the fraction of the blue with respect to the blue and white. And then the air is really not that important in this talk today, but you can see it. So the mathematical models have to describe how water flows, maybe other elements flow, water vapor and so on. So they also have to describe how the liquid and ice phases change the position. So lots of good mathematics. So many of you might be familiar already with the Stefan problem for freezing, but I thought I would just describe this one in one slide. Augusto Vicentin, who is in Trento, right, wrote wonderful books, and many other people wrote a lot of theory on well-posedness of the so-called Stefan problem. So here I'm showing to you this thermal energy conservation equation, and the key thing to notice is that there are two variables, W, which is the enthalpy, and theta, which is the temperature. And they're connected by a relationship, which I wrote not with an equality sign, but with a belongs to sign. And that will become important when you look at the relationship between theta, so temperature, and W, written as a multi-valued graph. So a lot of the work I do involves multi-valued graphs. And it looks pretty scary because people are like, well, so how do you deal with an inclusion rather than an inequality? But the fact is that there really is an equality if you look at other variables that describe the state of the matter. So in particular, water fraction and temperature together describe the state of the matter. Okay, so there's a bijection between enthalpy and these two. You cannot just use the temperature, but people usually write it PDE only in terms of temperature and enthalpy, and that's why you need the inclusion symbol. That's a common thing that people use also in a lot of variational inequality problems where there is, let's say, a Lagrange multiplier that is a selection out of a multi-value graph that makes things work. So an example of how the solution to the Stefan problem behave is the enthalpy in blue, you can see, takes a jump when you warm the originally frozen portion from left to right. Temperature in red remains continuous. And the reason why the enthalpy jumps is also because, in the sense, the model is really written in the sense of distributions. And the jump in the enthalpy occurs exactly at the same point where there's a jump in the flux in green. So you will see this movie again. Anyway, there are a lot of phase transition models. This one is probably the easiest one to start with, and it's driven only by the temperature changes. For snow, however, we'll talk later about mass-driven phase transition. All right, so more inclusions. You've seen this model before. Here's another example with so-called solubility constraints. So one mass conservation equation, but a component that goes between two phases with different saturations. And again, you would write this as them being together. So maybe C would be in the graph G of theta and saturation. But anyway, the scary inclusion can be always explained by the variable that's missing from the PD, but it's really somewhere underlying. So it's not such an impossible thing to really handle. However, when you have a coupled model, such as the one for snow that I built, you have to look carefully at the coupling. Another way to see this model is you would have this subgradient of the indicator function that's not the characteristic function of this context set in which the concentration should belong. So this is a parabolic variation inequality. This model is coupled to this one, and it's really very interesting how you would do it. How you would do analysis, and then how you would do numerics. The numerics, as I said, we are looking always at rectangular grids for easiness. And then, of course, no free boundary will necessarily obey our grids, right? It will never align with the grid. So many people consider other approaches than what we do and what traditionally people use, which was the P1 approaches. But typically, for example, these other approaches could be phase field approaches, or they would solve the model with some high order method in the one phase region and in the other region, and try to do some kind of interface tracking by some high order method, level set methods or whatnot. All these methods are really great. However, for the applications that you've seen, the scale, pore-scale, they don't really scale well for us. So that's why we have used the next approaches. And then, as I said already, the PDEs are posing this in the sense of distribution, so the regularity is pretty low. Like enthalpy is not continuous, and temperatures are continuous, but like they are in H1, and also continuous across the interface, but that's about all you have. All right. So what we do is we also write the problem fully implicitly in time and use Newton's method, which means in practice, because of the variational equality involved, semi-smooth Newton method to deal with this. All right, and that's all very efficient, but everything depends on how you choose your Fermat unknowns and how you work with it. All right. Okay, so then this is the permafrost picture cross section. You see here the top soil called the active layer. You see an ice wedge that's underneath. So these ice wedges faded. You see some other portions of the soil, and the pore-scale, that's what that soil looks like. There are grains, there's water and ice, and maybe there's some pockets of air. You also see the temperature. Typical temperature behavior is, since it responds to what's happening yearly, right? It's cold, then it's warm, cold and it's warm, and again it's cold and warm. The temperatures go from very cold, the red one is the temperature, to warm again, then they go back and they go back. The point is, at a certain depth, the temperatures remain fixed. They don't really change much because this input of warm fluxes is not enough to change the temperature below a certain level. But what's important is the level, the depth of this top active layer. And you see here the picture. With the surfaces warming, the active layer extends. This means ice falls. This means ground subsides, slides down to the valley, and we have now, of course, since these days we might not all agree on whether there is climate warming or not. We have here a comparison of the depth of the active layer with or without climate warming, so you can be the judges of what could happen. All right, so mathematics of how you connect the pore and Darcy scale is interesting because, okay, so let me first show you the Darcy scale model and the pore scale. So pore scale, we have heterogeneous Stefan problem, which you have seen already. And at the Darcy scale, you have a model that has very smooth solutions compared to this one, right? It's because you're averaging the phase transition over a lot of different phases and also over many different freezing temperatures. So at the pore scale, you have rock pieces that don't freeze, and then you have different sizes of pores. And in large pores, you have freezing temperatures close to the usual, but in very tiny pores, the water sometimes doesn't freeze. So that goes to properties of water that doesn't really freeze in tiny pores or when it's very salty. So there's a big dependence on those freezing temperatures that I'll describe in a minute. So part of our work was identifying this connection, but before that, just hats off to a lot of the work that was done on Stefan problem with the traditional P1. So P1 means for temperature and enthalpy approaches, and how our approach, which is here, varies and how it has advantages. We get actually pretty good behavior with the P0, so piecewise constant approach. All right. here's some convergence results as typical for the Stefan problem because of this discontinuity and low regularity. You don't get more than, let's say, I don't know, 1/2 order of accuracy for the enthalpy, but you can get pretty much close to order 1 in the temperatures. In the permafrost, you get better because it's a smooth relationship, even though it has a corner, but we get better behaving solutions. You see, they're much smoother. All right, now upscaling, which was the key point of my presentation. When you have a PDE like that, upscaling means you have to average this portion and, well, average. Homogenization is the mathematically correct term, and you have to average this portion. Now, this is, of course, nonlinear, so there are some difficulties there. There are 2 different things you do. You upscale this portion, and that's what produces the smooth graph that I mentioned between enthalpy and temperature. And then you upscale the conductivity. Now, the challenge here is that this upscaling gives you results different depending on the geometry of the pores. So again, this is interesting how that happens. So without considering the fact that in tiny pores we don't have the same freezing temperature as in large pores, you would just have an average, one relationship between the temperature and water fraction. But because we know that in tiny pores, water doesn't freeze until it's very, very cold, you have a lot of step functions, which you can then, fit to some kind of a slope relationship. And what I mentioned, the physical behavior of the different freezing temperature, it's also known as the Gibbs-Thomson relationship. Not quite the Gibbs-Thomson, but for the purposes of this talk, let's assume that it is. Now, I want to give kudos to one of my students who was actually an undergraduate at the time, who listened to me about all this, and so like, so do we really know that ice always forms in the center of the pores rather than sticks to the grains? And he said, so he did his physical experiment in his freezer. So it's actually pretty nice, and then followed up with the simulation. So anyway, I think it's really wonderful to have brave people. I would be too afraid to do physical experiments because I was not really all that accurate in physics labs. But anyway, he did it. It's just that youth is always brave, and that's great because without you guys, we would not have progress. Now, this is an example of a pore-scale with ice and grains, where we did the simulation of the water freezing temperatures, and you see here the water arises around the grains first, rather than, and then the ice remains in the middle of the pore. So when you upscale, you will have a big difference depending on what you assumed about the initial conditions and other boundary conditions and whatnot. So the question is then, so what do you do to overcome it? Because you would have a different upscale quantity for different simulations, really just multi-dimensional uncertainty. So one way around this is to look at, and I will come back to look at some neural network derived relationships and try to fit them rather than some algebraic. This is what happens when you upscale flow and the energy together. Now, there has been a lot of work done on homogenization for single physics model. Not that much for coupled physics, because then even if you started with linear problems at some lower scale, if they're coupled, then the whole thing becomes nonlinear. So the way we do it for the transport and flow is we solve the problem at the pore scale, then we follow up with the flow problem. Of course, water only flows around the ice, not through the ice. So then they are very tightly coupled. You can have a lot of different approaches to get those. Now, one way around getting these pore scale realizations of the ice and water is to use Monte Carlo, the Markov chain Monte Carlo method with some kind of impulse derived model. So that's what we did instead of the traditional models, because they are actually producing more coherent view rather than a gazillion of simulations. We would, do 10,000 simulations that they would always have the same, more or less the same qualitative behavior. Then we upscale to get the Darcy level thermal conductivities. Then we also solve H in the collection of the different levels. It turns out that the thermal convection is not so important. In the ice liquid, it might be very different with gas, but not here. I mean, if you use the correct coefficient. So then in the end, we decided to build a surrogate model with neural network. And here's another picture that another undergrad did with, you see here in green, some pockets of air. So he derived a Hamiltonian that was useful in simulating the distribution of ice, the liquid, and the air phase in the force media based on some macro scale properties that then he fitted that. All right, so this is the neural network effort. We tried many different things. So, typically geophysicists, and nothing wrong with geophysics, but they would take a bunch of data and then they would fit an algebraic model to it, and like some kind of a polynomial. We didn't find, for example, for this blue curve to give a really reasonable fit. So we decided to use a variety of data and use multidimensional, like essentially nonlinear regression with neural networks, but trying to find the right correlation. See, I was hoping once we have the data from these 10,000 simulations, we can make sense of them. But in the end, neural network regression gave us something that was probably just as good as maybe a polynomial fitting model. I don't know. So we have new tools, but we come up with eventually with maybe the same kind of level of. Okay, now BL model. I'm not giving equations for BL. A lot of people here are working on BL, so So that's flow and mechanical deformation. I always was fascinated by the question, how does permeability change when in BL you have displacement of the force medium, and how does the permeability kappa depend on velocity? How can you upscale that? So, and then how you do it at force scale, because when the grains move, it's not so easy. In small porosity, in typical porous medium is maybe 20% porosity, 30% porosity in sand, but in clay it's much smaller. So it's not so easy to visualize these cutesy particles traveling. That's not porous media in the soil. So we set up to use discrete element method generated force scale geometries under load. So here you have two different geometries that were created at, I think, 10 kilopascal load and 100 kilopascal load with different flow patterns that result from it. Of course, we did it in steps. So those familiar with the discrete element method, you use some kind of first principle physics to describe the movement and to the quasi-stationary position of the particles like these with respect to each other when there's an external load. You have to assume things about friction and whatnot. Anyway, the fascinating thing was how the upscaled results, so then follow up with upscaling of the flow, how they depend on the load. And with load going up and going down, we have different results, which of course everybody knows. It's called history. So there's lots of still work in progress on this, but we're pretty happy to get this relationship more or less also fit to certain curves. And by the way, I thought we would have a breakthrough that would change the world, but in fact that dependence was not all that strong. So in the end, yeah, it's not a very strong dependence. All right. Last couple of statements about the now coupled models. So now the thermal and the hydrological and mechanical model coupled together, you see here. So, okay, one of the philosophical things that I've always thought is good is that how do you move to multi-physics from a single physics model? How do you work with it? How do you prepare your single physics code to be robust when you move to multi-physics? So one way to do it is to push it to work well with heterogeneous data in layers that have very different properties in these layers. So if you have a numerical method that's stable and accurate for those, then you can go to multi-physics more safely. And this is an example of when we looked at the different layers with different variables and showing what you can do. You can prove also in a coupled model convergence of iteration under various assumptions. Already for BO, and there was a parameter there that we had to assume was positive rather than just non-negative, but still there's some hope that one can both prove and then check numerically that things work. And I mentioned earlier that depending on which primary variable you choose, you will have, you can take larger steps. You can see here large time steps in red if you use the enthalpy as a primary variable, and fewer iterations, more robust Newton solver than if you use temperature as a primary unknown. So lots of work again is in progress. Here's a cartoon of, again, a heterogeneous problem. Lamé coefficients in elasticity also depend very strongly on temperature. And ice is a very interesting material. The Lamé coefficient change dramatically at freezing, of course, but also they are not monotone depending on the temperature. So yeah, it's absolutely, so we had to use textbooks from engineering rather than postulate our own laws. And we were really stunned by the variety. So here's an example how some of the, in the coupled model, how the displacement and pressure change. And you can see a lot of almost continuous properties when you have a layered medium. And of course, you can have fun and post-process some of these results, which one of my wonderful students, Madeleine Bora, did and post-process. So to show what's really happening. All right, last thing, snow. Because I showed you, you saw my pictures at the beginning on a glacier and also skiing. So I do hope in another 100 years, when I still go skiing, that I will still be able to ski. And I'm sure you want to, play with snow. Yeah. So it's important in permafrost zones as well as anywhere to look at snow. So here you have soil, snow layer, which is probably very thin compared to the soil layer. You have also air, and you have to account for a lot of different environmental factors that affect how snow, goes from being dry to being wet to being, there's something called metamorphosis of snow. And there's a lot of air turbulence, the dry air that takes some of that energy away. Lots of interesting, fascinating things. But it's so complicated that at the very beginning, we looked just at the boundary condition that we did, and that average the boundary condition, including as all the environmental factors in that variable x of t, which depends in time. And just to show you how variable it is, this is a picture from the Arctic, how some of those, the air temperature changes, it's not the trend I'm curious about, it's the variability, as you can see, is quite daunting. So again, another neural network model that we built, trying to get from data some kind of a relationship for that reduced depth average model. And that's one approach. Another approach is to use the decomposition. Of course, here in Box, people, they're the best people in the world who have worked on heterogeneous domain decomposition. And so that's what we are doing right now. Last but not least, I want to show you just a snow model. At the beginning, I told you the temperature-driven phase transition is one thing. Mass-driven transition is another thing. When you couple together, things get really interesting. So you have here two different models. This one is mass-driven. This one is the energy-driven. They are coupled together by by the ice present in S, and then you see here the variables again use graph. The position of this graph, so the position of this constraint graph depends on the temperature. So there's a lot of coupling here. When you simulate them, though, just let's say you start from some initial conditions and it's an isolated system, no forcing in either of the equations, and not much is happening. In fact, it's excruciatingly slow to get any result, which is partly why some of those models are frustrating. Of course, I'm working here on a very small centimeter scale, so something is happening. I start with some ice block in the middle, with some ice there, and you can see how the temperature is coupled to this problem. In realistic 2D models, also not much is happening. And here's why, because you really do need, for snow metamorphosis, you need these strong solar radiation effects. You need dry air to come, and you know about sublimation, right? You start with a lot of nice snow in the evening. Yes, I can go skiing. And next morning, you get up and there's almost no snow on the ground, even though there's no water to drink. It's because all of that water vapor went back to the air. So one success from a lot of the upscaling of these models has been that geophysicists in the Arctic measure snow conductivity based on its density. We were able, with our upscale model, to do quite well with one of the models that we based just on the presence of the ice. So anyway, I will leave you with this. And by the way, there is permafrost in the Alps. And I think Milan is somewhere right here. Right, a little here, right. So there is, on the Swiss side, the closest one to Milan, but there's a lot of permafrost there, and the Swiss people and lots of European networks have been studying and collecting data on the thawing of permafrost. And so again, I hope we'll still have the snow to ski on and to keep the water for the summers. Right. So thank you.